In this short video, we'll look at the van der Waals equation, which is one of many real gas equations, but it's the common form of the real gas equation that you see in a general chemistry class. And it's a good idea to start with the ideal gas equation and then build up to the van der Waals equation. So we know that the ideal gas equation is the product of pressure and volume is equal to the product of moles, the ideal gas constant or the ideal constant of the state equation, and temperature. But the ideal gas equation assumes that there's no interaction between the gas molecules, which is not necessarily true. It assumes ideal behavior. So what does ideal behavior mean? Ideal behavior means relatively low, not too low, so there's definitely a sweet spot, but relatively low pressure and temperature. Not frigid temperatures, because then you'd have a real gas again, but relatively low pressure. The van der Waals equation, or the real gas equation, or this particular real gas equation, considers the fact that under certain conditions, high pressure, for example, or low temperature, gas molecules can interact with each other through induced van der Waals forces. And the absolute size of each gas molecule is not negligible, so there's alterations to volume that we have to consider, there's alterations to pressure that we have to consider. So this is ideal. The real, or the van der Waals, there's going to be a correction to pressure and there's going to be a correction to volume. So we'll call this real. This is ideal. So this will be our van der Waals equation here. Okay, so there's going to be a correction to pressure, which is going to be a positive correction, and it's going to be proportional. Well, it's going to be a correction that's proportional to the square of concentration. So concentration, we know, is moles per unit volume. So concentration squared is moles per unit volume squared. And the constant of proportionality is called A. So we'll see shortly where this constant of proportionality, or rather, we'll see where the concentration squared factor comes from. The volume has a negative correction, and it's proportional to moles of gas, N, and another constant of proportionality, B, where A and B are constants. They're relative to a certain gas, and typically the values of A and B will be provided to you in any assessment. You wouldn't have to a priori know these values. Okay, so this is the ideal versus the real gas equation. Let's consider where this correction term comes from here. Well, let's say you had a gas A, and we're considering two members of that gas. So two members of a gas A, so two representative constituents of A. Let's say this is the first A molecule, this is the second A molecule. Then we can remark that if I'm A1, the pressure that I experience, or the pressure that I'm capable of exerting, is influenced by the concentration of A2. So I know that the pressure of A1 depends on the concentration of A2, and likewise I can say that the pressure of A2, because there's a relationship between A1 and A2, mutually depends on the concentration of A1. So considering an adjacent setup where you look at one member of the gas and just one adjacent member, we have two concentration considerations. So this is concentration squared. So this is the origin of this concentration squared term here. The origin of the volume correction over here is much more simple to appreciate, although that was pretty simple to appreciate also, to be honest. But we have to subtract a volume because of the presence of the constituents themselves. So for example, a real gas has a relatively high pressure compared to an ideal gas. So no longer can I assume that the gas molecules or the size of the gas itself is negligible. I have to incorporate the volume occupied by each member of the gas itself. So for example, the presence of A2 prohibits A1 from occupying the volume taken up by A2. So A2 has a definite size, and the volume that A1 can occupy is the total volume minus the volume already occupied by A2, and vice versa. The more A2 I have, the less volume there is remaining for A1 to occupy. So that's why this correction is proportional to moles. And the factor B depends on the relative size of the gas, for which B is a constant. Okay, we'll pause the screen and then we'll try a calculation. So here I'm going to calculate the pressure of this system, so 10 grams of CO2 gas in a 100 centimeter cube container at 25 Celsius. I'm not really interested in following significant figures that much. So don't look at another one of my videos where I'm a bit more litigious about significant figures. But the point here is I want to look at what the ideal gas equation would say the answer to this problem is, and then what the Van der Waal equation would say the answer is. See that there's a difference and see why one is unreasonable. So we'll start with the ideal gas equation first. So if I calculate the pressure, P is nRT over V, that's our ideal gas equation. And if I plug the numbers in, then N, well, I've got grams, so I need to convert that to moles. So 10 gram, I convert that to moles by setting 1 mole of CO2 equal to its weight in grams, which is 44.01. So I cancel the formula weight of CO2 here with the input mass of CO2 here. I've got my ideal gas constant, 0.8206 liter atmosphere 1 mole Kelvin. And then I have temperature. Temperature has to be in Kelvin, so I add 273. Strictly speaking, I should add 273.15 because it's an exact number. I'm just going to add 273 to it, so 298 Kelvin. So that's T, and then I need volume down here, so I can just stick volume over here. And my volume, in fact, I won't stick it over here because it's not in the right units. So I'll have to divide the whole thing by volume. So I need volume in liter. So I've been given 100 centimeter cubed. We need to get that into liter. So I know a milliliter is 1 centimeter cubed. And I know the relationship between liter and milliliter, it's a 1 to 1,000. Okay, so finally I have the correct units. I crank away at that on my calculator and I get a value. Pressure is equal to 55.6 atmospheres. And there's the problem. The number is what it should be, but I can't use this equation to calculate a number that large. So anything beyond around 1 or 2 atmospheres, you're really on dicey territory using the ideal gas equation. So we'll keep this value in mind. We'll recalculate using the van der Waals equation for real gases. So we've just seen that the ideal gas equation for this problem returns a value of 55.6 atmospheres, clearly too large to be taken seriously. So we come back again for a second attempt using the van der Waals equation, which we've stated already has a correction to pressure and a correction to the volume term. We need to isolate pressure. So first thing, we'll take the volume downstairs, so we'll have pressure equals nRT over V minus NB. So we've taken this term, cross multiplied it down here. And then we need to subtract the correction to pressure from both sides, minus A N over V squared. So this is now the cross multiplied expression to isolate pressure. We can plug our values in. You'd have to be provided with A and B for carbon dioxide gas, but I'm going to furnish you with those values. So we've got moles, which I'm going to essentially just calculate moles as we did before. So we've got 10 gram of CO2. I need mole, so by definition I know a mole of CO2 is the weight of CO2 in gram. There's my moles. My R is 0.08206 liter atmosphere per mole Kelvin. My temperature is 298 Kelvin. My denominator, recall, was, what was this value? Well, it's essentially, just to save me a little bit of room, it's essentially 100 milliliter, so it's 0.1 liter. So actually, let's write that over here. Save a bit of space. Okay, so everything except 0.1 liter is my numerator here. My denominator is 0.1 liter, but I've got to subtract NB. So moles, now I've run out of space. So I will go ahead with plan A. So lesson to self, always follow plan A. So let's divide the whole thing by, sorry, not divide. Yes, divide the whole thing here. Okay, so 0.1 liter minus moles. Now, if you actually do 10 divided by 44.01, that will give us the moles. So I'm going to tell you that that is 0.2272 mole of CO2. So that's V minus N, but N is multiplied by B. B is a constant, which if you look up, it's 0.043, and the units are liter per mole. Okay, so this is V minus NB. N here is just 10 divided by 44.01. Okay, so that's our B minus NB here. And then from this quotient here, I've got to subtract this correction term. So let's do minus, and then it's concentration squared. So the moles we've said here was 0.2272. The volume we said here is 0.1 liter. The whole thing has to be squared because it's N over V squared. And then I multiply it by A. Now A, sorry, this is a bit squished at the end. A is 3.59. And the units are liter squared atmospheres per mole squared. Okay, so it's squished, but it's intact. We have N R T divided by V N minus NB. And then we have subtracted this term here, A multiplied by N over V squared. If you plug everything in, it will give you pressure is equal to 43 atmospheres. Recall from the previous slide that we had 55.6 atmospheres when we used PV is nRT. So we get a dramatically different value, the correct value in this case, and we've learned that the ideal equation on this occasion, when we used it incorrectly, overestimated pressure by 29%. It won't always be 29%, it was 29% here. Clearly, you have to be given some information during an assessment when you use the Van der Waal equation. You would never be expected to memorize A or B values for every gas. Takes a couple of seconds longer to calculate, and you would use this equation preferentially if you had a higher pressure system or a very low temperature system where the gas had condensed a bit more. So be on the lookout for when to use the appropriate gas equation.